Hello! In this video, we are going to prove the following theorem. A function f from a comma b to r is Riemann integrable on a comma b if and only if, for every epsilon greater than 0, there exists a delta greater than 0 such that if p and q are any tagged partitions of a comma b whose norms are both less than delta, then the absolute value of their difference of the Riemann sums is less than epsilon. So this is essentially the Cauchy criterion for Riemann integrability. Now at this point, we know that every Cauchy sequence of real numbers converges to some real number, and we're going to be using that in proving this theorem. Another property of convergence sequences that we're going to be using is the following. Suppose xm is a convergent sequence of real numbers, a is a real number, and xm is greater than a for sufficiently large m. Then the limit of the sequence is greater than or equal to a. So now let's remind ourselves of the definition of the Riemann integral. To say that f is Riemann integrable on a comma b means the following. It means there exists a real number L such that for every epsilon greater than 0, there exists a delta greater than 0 such that for all tagged partitions P of a comma b whose norm is less than delta, the absolute value of the Riemann sum minus L is less than epsilon. Now we have proven that this real number L, which satisfies this statement, is unique. And we call L the integral of f, and we denote it like this. Okay, so now let's get into proving this theorem. Now we're trying to prove a statement containing if and only if. And to prove that, we're going to prove if f is Riemann integrable on a comma b, then this statement after the if and only if is true. And then we're going to prove if the statement after the if and only if is true, then f is Riemann integrable on a comma b. So we're first going to prove the forward direction. And to prove the forward direction, let's suppose f is Riemann integrable on a comma b. And from here, we're trying to prove that the statement after the if and only if is true. And since we're trying to prove a statement about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. From here, the whole goal is to find a delta greater than 0 such that this is true. Now, since f is Riemann integrable on a comma b, this means that this statement is true. And this statement works for every positive real number. So in particular, it must work for the positive real number epsilon over 2. So, taking epsilon here to be epsilon over 2, well then, there exists a delta greater than 0, such that for all tagged partitions of a comma b whose norm is less than delta, we have that the absolute value of the Riemann sum minus the integral of f is less than epsilon over 2. Now remember, we have been trying to find a delta greater than 0 such that this is true. And the claim is if we take delta to be the delta that we have in our proof, then that statement will be true. So to prove this statement, let's give ourselves two arbitrary tagged partitions, P and Q of a comma b, whose norms are both less than delta. And from here, we can show that this inequality is true. So let's start out by writing the left-hand side. And what we're going to do is we're going to add and subtract the integral of f. And now, applying the triangle inequality, the absolute value of this guy is less than or equal to the absolute value of this guy plus the absolute value of this guy. But then we can replace this guy with absolute value of the Riemann sum minus the integral, and it will be the same. But then, since P is a tag partition of a comma b whose norm is less than delta, well, it follows that the absolute value of its Riemann sum minus the integral is less than epsilon over 2. So this guy is less than epsilon over 2. And also, since Q is a tag partition of a comma b whose norm is less than delta, it follows that the absolute value of its Riemann sum minus the integral is less than epsilon over 2. So this guy is less than epsilon over 2 as well. And therefore, the sum of these two guys must be less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. And so this shows that the absolute value of the difference of Riemann sums is less than epsilon, which is exactly what we wanted to show. So we have proven that the statement which comes after the if and only if is true. So that proves the forward. Now we're going to prove the converse. We're going to prove if the statement after the if and only if is true, then f is Riemann integrable on a comma b. So to prove that, let's suppose that the statement after the if and only if is true. From here, the whole goal is to show that f is Riemann integrable on a comma b. Now the idea is we're going to construct a Cauchy sequence of Riemann sums. And therefore that sequence of Riemann sums will converge, and we're going to prove that the value that that sequence of Riemann sums converges to is in fact the integral of f. So to do that, since we ran out of room, let's move back up to the top. Now, as preliminary work for constructing our sequence of Riemann sums, what we're going to do is we're going to consider the set of positive integers, so 1, 2, 3, and so on. But now we consider the reciprocal of each positive integer. And what we're going to do is we are going to apply this statement to the reciprocal of each positive integer. So in general, if we consider a positive integer n, well then 1 over n is greater than 0. And since 1 over n is greater than 0, and this statement works for every real number greater than 0, then in particular it must work for 1 over n. And therefore, there exists a positive real number, I'll call delta n, such that if p and q are any two tag partitions of a comma b whose norms are both less than delta n, then the absolute value of the difference of their Riemann sums must be less than 1 over n. So what this is essentially telling us is each positive integer n can be mapped to a positive real number delta n, which has this property. So 1 gets mapped to delta 1 with this property, 2 gets mapped to delta 2 with this property, 3 gets mapped to delta 3 with this property, and so on. So we have a sequence of positive real numbers, delta 1, delta 2, delta 3, and so on and so forth. And each term in that sequence satisfies this property. Now, the claim is that we can adjust this sequence so that it's a decreasing sequence. And to do that, we're going to reconstruct this sequence recursively. And to do that, well, at the first step of the construction, let's choose delta 1, so that delta 1 has this property. So now, let's suppose at the nth step, we've chosen delta n with the same property. So now, for the n plus 1th step, we are going to choose delta n plus 1 with the same property. But also, we're going to make sure that we choose delta n plus 1 so that delta n plus 1 is less than or equal to delta n. Because that will guarantee us that we are recursively constructing a sequence of positive real numbers which all satisfy this property, but also it's a decreasing sequence. Now, of course, 1 over n plus 1 is greater than 0. So, since this statement works for every positive real number, then in particular it must work for the positive real number 1 over n plus 1. So in that case, there must exist a delta greater than 0, such that if P and Q are any tag partitions of A comma B whose norms are both less than delta, then the absolute value of the difference of their Riemann sums is less than 1 over n plus 1. So now we just take delta n plus 1 to be the minimum of delta and delta n. Well then, delta n plus 1 is both less than or equal to delta and less than or equal to delta n. But also, delta n plus 1 satisfies the same statement that delta satisfies. Because if we give ourselves two arbitrary tag partitions, P and Q, of A comma B, whose norms are both less than delta n plus 1, well then, since delta n plus 1 is less than or equal to delta, their norms are both less than delta as well. And therefore, we can conclude that the absolute value of the difference in Riemann sums is less than 1 over n plus 1. And so this shows we can recursively construct this sequence so that every term in the sequence has this property, and it's a decreasing sequence. So now, for each positive integer n, we choose a tag partition Pn of A comma B, whose norm is less than delta n. And so just like how we mapped each positive integer n to a positive real number delta n, which has this property, we are now mapping each positive integer n to a tagged partition Pn of A comma B, which has this property. Now, if we consider two arbitrary positive integers, m and n, where m is greater than n, well then, by choice of these partitions, it follows that the norm of Pn is less than delta m, the norm of Pn is less than delta n. But since m is greater than n, and the sequence of delta n's is a decreasing sequence, well then, we must have delta m less than or equal to delta n. So both the norm of Pn and the norm of Pn are less than delta n. So because their norms are both less than delta n, we can conclude that the absolute value of the difference of their Riemann sum is less than 1 over n. And so this is what we have for any two positive integers m and n where m is greater than n. We have that this inequality is true. And from here, it follows that the sequence of Riemann sums of f with each of these partitions will be a Cauchy sequence of real numbers. And to see how this is a Cauchy sequence of real numbers, well, what that means is we would like to prove the following statement is true. we can prove that this statement is true, which is what it means for this sequence to be a Cauchy sequence by definition. So if we wanted to prove this statement, we would first give ourselves an arbitrary epsilon greater than 0, and our choice of h would be to choose h so that h is a positive integer greater than 1 over epsilon. And with this choice of h, we would like to show that this statement is true. And to prove this statement, we would give ourselves two arbitrary positive integers, m and n, such that m is greater than n is greater than or equal to h. And from here, we would like to show that this inequality is true. Now, since m and n are positive integers such that m is greater than n, well, that implies this inequality is true. But then, since n is greater than or equal to h, if we take the reciprocal of both of them, it flips the sign of the inequality. So we get 1 over n is less than or equal to 1 over h. But then, since h is greater than 1 over epsilon, if we switch h and epsilon, we get 1 over h is less than epsilon. And so this shows that this guy is less than epsilon, which is what we wanted. So we have proven that this statement is true, which verifies that this sequence is in fact a Cauchy sequence of real numbers. And because it's a Cauchy sequence of real numbers, it must converge to some real number. We're going to say that L is the limit of this sequence. Now, let's fix some arbitrary positive integer n. Well then, for every positive integer m greater than n, we know that this inequality is true. In other words, we can think of this as a sequence from n equals 1 to infinity. So this is a sequence where we can think of m as being variable, but n is just a fixed constant. The idea is that if m is sufficiently large, then every term of the sequence is less than 1 over n. Therefore, if this sequence is convergent, then the value it converges to must be less than or equal to 1 over n. Right? That's precisely what this first fact is telling us. Well, actually, since this sequence converges to L, it follows from properties of limits that this sequence will converge to absolute value of L minus the Riemann sum of f with Pn. Or in other words, that's equal to the absolute value of the Riemann sum of f with Pn minus L. So the limit must be less than or equal to 1 over n. So now the claim is that L is the value for the integral of f. And to prove that, we would like to prove that this statement is true. And since we're trying to prove a statement about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. From here, we want to find a delta greater than 0 such that this is true. So what we're going to do is we're going to choose a positive integer k such that k is greater than 2 over epsilon. Well then, since k is a positive integer, we can consider the positive real number delta k. The claim is if we take delta to be delta k, then this statement will be true. So taking delta to be delta k, we're going to show that this statement is true. And to prove this statement, let's give ourselves an arbitrary tag partition P of a comma b, whose norm is less than delta k. From here, we want to show that this inequality is true. Well, to show that this inequality is true, let's start off by writing the left-hand side. And so, since k is a positive integer, we can consider the tag partition pk. So what we're going to do is we're going to take what we have inside the absolute value, we are going to add and subtract the Riemann sum of f with pk. Then, by the triangle inequality, the absolute value of this guy is less than or equal to the absolute value of this guy plus the absolute value of this guy. Now, we know that the norm of p is less than delta k, and also, replacing n with k here, we know that the norm of pk is also less than delta k. But also, replacing n with k here, we know that delta k is a positive real number, such that if we have any two tag partitions of a comma b whose norms are both less than delta k, then the absolute value of the difference in their Riemann sums must be less than 1 over k. So in particular, the absolute value of the difference in the Riemann sums of these two partitions must be less than 1 over k. So in other words, this first guy is less than 1 over k. But then, what can we do with this guy? Well, this inequality is true for every positive integer. So replacing n with k, we have that this guy is less than or equal to 1 over k. Because this guy is less than 1 over k, and this guy is less than or equal to 1 over k, it follows that the sum of these two guys must be less than 1 over k plus 1 over k, right? Because in general, when we have any four real numbers, a, b, c, and d, where a is less than b and c is less than or equal to d, this will imply that a plus c is less than b plus d, right? So that's really what we're using here. That's why we're less than 1 over k plus 1 over k, which is equal to 2 over k. But since we chose k so that k is greater than 2 over epsilon, well, if we swap k and epsilon, that gives us 2 over k is less than epsilon. And so we have shown that this guy is less than epsilon, which is exactly what we wanted. So we have proven this statement, which proves that this value L that we have here is in fact the integral of f. And therefore, f is Riemann integrable on a comma b. And so this completes the proof. And so yeah, that's pretty much it for this video.